Most of the statistics we have discussed thus far, such as the z-test and the various t-tests, help us assess the differences in the means. While these measures prove useful in certain situations, but they do not inform us about the relationships between two data series. The scatter plots might be the easiest way to visualize the relationship between the two variables. Let's look at an example. Here are the 4 data series. The tools we have learned thus far will help us calculate the mean and the standard deviations, and using z-test or t-tests, we can evaluate whether the means are statistically equal or not. However, if we want to know how these data series are related to each other, we can visualize that by using a scatter plot. A scatter plot uses dots to represent values for 2 different numerical variables. So this point on the plot represents 1 for variable 1 and 2 for variable 2. Similarly, this point represents a value of 8 for both the variables. The dots in a scatter plot not only report the values of the individual data points, but also the pattern when the data points are taken as a whole. So, if we were to fit a straight line through these data points, it might look something like this. We can fit a straight trending line through most of the data points, which suggests a strong positive linear relationship between the two variables. Which means, as we increase variable 1, variable 2 increases as well. Similarly, the scatter plot between variables 1 and 3 shows that they are linearly negatively related. It seems we might not be able to fit a straight line through the dots for the scatter plot between variables 1 and 4, so we have a nonlinear relationship between the two. In contrast to scatter plot, which graphically depicts the relationship between the two data series, covariance and correlation expresses the same relationship using a single number. Covariance measures the directional relationship between the two data series. A positive covariance means that the two data series move together, while a negative covariance means they move inversely. The prefix co defines a joint action, and the variance refers to variation or change. So the covariance summarizes how the variables change in relation with each other. Here is the formula to calculate the covariance. X bar and y bar are the means of the variables x and y, and n is the number of observations. Let's calculate the covariance between variables 1 and 4. The first step is to calculate the means. Second step is to find the deviations from the means. And in the third step, we calculate the product of the deviations. Next, we add the product of the deviations. Finally, we calculate the covariance by dividing the sum of the deviations by n minus 1. While covariance is a useful measure to find the direction of the relationship between the two variables, but since it can take any possible value, the covariance does not provide useful information regarding the strength of the relationship. This is where the correlation proves to be an important measure of not only the direction, but also the strength of the relationship between the two variables. A correlation coefficient can have a maximum value of 1 and a minimum value of -1. A correlation coefficient greater than 0 indicates a positive linear association between the two variables. When one variable increases, the other tends to increase as well. A correlation coefficient less than 0 indicates a negative linear association between the two variables. When one increases, the other tends to decrease. A correlation coefficient of 0 indicates no linear relationship between the two variables. If all the points on the scatter plot lie on a straight line with a positive slope, then the correlation between the two variables is +1 as shown in this figure. Similarly, if the plotted observations fall on a straight line and the line has a negative slope, then the correlation between the two variables will be -1. Here is the formula for computing the sample correlation coefficient. The correlation coefficient R is the covariance between the two variables x and y divided by the product of their sample standard deviation, Sx and Sy. Similar to covariance, the correlation coefficient is a measure of linear association. The correlation coefficient, however, has the advantage of being a simple number with no unit of measurement attached. It has no units because it results from dividing the covariance by the product of the standard deviations. Let's look at an example. The following table presents the individual observations on countries' annual average money supply growth from 1980 to 2012 as denoted by Xi, and individual observations on countries' annual inflation rate for the same period as denoted by Yi. We can add all of the observations together and calculate the mean by dividing the sum by n. Next, we can calculate the product of the deviations from means for x and y data series. Adding the product of the deviations and dividing by n-1 gives us the covariance. Next, we calculate the sample variances for the two data series by adding the squared deviations and dividing by n-1. Standard deviations are calculated by taking the square root of the variances. Lastly, we can plug in the numbers for covariance and the two sample standard deviations to calculate the correlation coefficient. The correlation coefficient of approximately 0.91 indicates a strong linear association between long-term money supply growth and the long-term inflation for the countries in the sample. The correlation coefficient captures this strong association numerically, whereas the scatter plot in this figure shows the information graphically. Correlation measures the linear association between the two variables, but it may not be always reliable. Two variables can have a strong nonlinear relation and still have a very low correlation, as is the case with these two variables. Even though these two variables are perfectly associated, the correlation between them is zero. Correlation also may be an unreliable measure when outliers are present in one or both the data series. Outliers are small number of observations at either extreme of a sample. These observations are outliers. If we compute the correlation coefficient for the entire data sample, that correlation is negative 0.035. If we eliminate these two outliers, the correlation is 0.1489. As a general rule, we must determine whether the sample correlation changes by removing a few outliers. But we must also use judgment to determine whether these outliers contain information about the two variables' relationship and should thus be included in the correlation analysis. Or these outliers contains no information, in which case the outliers should thus be excluded. A final note, correlation does not imply causation. Even if the two variables are highly correlated, one does not necessarily cause the other in the sense that the certain values of one variable bring about the occurrence of certain values of the other. In the next video, we will use Python to calculate the covariance and correlation.